Hi, everyone. Welcome to this webinar on migrating your Oracle database to Amazon Aurora, specifically Aurora Postgres using DMS and SET. By DMS, I mean the database migration service, and SET, I mean the schema conversion tool. Just a quick background about myself before we go ahead with this presentation. My name is Arun, and I currently work as a database engineer with the DMS SET team at AWS. I have helped a lot of customers migrate their databases from heterogeneously and homogeneously into AWS. And today we are going to talk about some of my learnings from what I've helped other customers and users migrating their databases into AWS. Migrating a database to the cloud can be a complex process, especially between heterogeneous database engines like Oracle and PostgreSQL. So in this session, I'm going to give you a quick introduction about DMS and SET, but the most important parts that we are going to kind of touch on is how do you take care of certain database objects and migrate them heterogeneously from Oracle to Postgres. So we learn the best practices for migrating Oracle 11G and 12C databases and schemas to Amazon Aurora Postgres with compatibility equivalents, leveraging both built-in Postgres capabilities and AWS ecosystem services. I'm going to concentrate a bit more on the built-in Postgres capabilities as the scope of this session. We'll look at detailed examples of table partitions, materialized views, triggers, and more as we keep going through this presentation. So quickly walking you through the agenda for today, like I said, we are going to introduce you to both the services in a very quick manner so that you know what AWS has got to offer to help you migrate your databases into AWS. And then we're going to talk about the migration playbook, which is a 350-page document helping you understand the best practices of migrating your Oracle databases to Postgres. We're then going to talk about the common feature comparisons between Oracle and Aurora PostgreSQL with examples. Basically, this is where we'll talk about different flavors of partitions and triggers and all of that. And then we'll wrap this session off with giving you a complete picture on what the schema conversion tool can do and help you automate some of these object migrations for heterogeneous database migrations. So to start off with an introduction on the database migration service and the schema conversion tool, database migration service is a service which helps you securely and easily migrate or replicate your data and databases and data warehouses into AWS. While the schema conversion tool helps you convert your commercial database and data warehouse schemas to open source engines. Schema conversion tool's biggest advantage is it helps you migrate all the secondary objects that the database migration service is not going to take care of. For example, things like referential integrity constraints, indexes, procedures, functions, and all of that are going to be taken care of the schema conversion tool. The schema conversion tool is something that you would install on an EC2 instance or a local machine before you start the data migration or replication using the database migration service. So we designed it to be simple. You can get started in less than 10 minutes. We designed it to enable near zero downtime migration, and we designed it to be kind of a replication Swiss Army knife. So you could replicate data between any of our supported sources and any of our supported targets. And the only requirement for you to be able to use the database migration service is to make sure either the source or the target resides within AWS. So you could come in from on-prem, migrate your database and replicate them to an AWS data center, or you could replicate them back to your own on-prem data centers from AWS to maintain your disaster recovery strategies and things like that. And it spans across multiple database engines and infrastructure as a service like RDS, EC2. So you can have your database anywhere, and as long as DMS as a service is able to connect to your database and read data from it and send data to the target, you should be able to use the service. Now, we talked about two different tools. How does the process look like at a high level when it comes to migrating both your schemas and your data that is residing in your databases? So The first step is obviously to use the schema conversion tool to copy and convert your source database schema into a destination or target database schema. You could very well use SCT to do that, even for homogeneous migrations to RDS. By homogeneous, I mean a like-to-like database migration, for example, Oracle to Oracle or SQL Server to SQL Server. One of the biggest advantages that we are going to talk about in the later part of this presentation is that SCT gives you something called an assessment report, and it's going to tell you how exactly, how difficult it is going to be moving your source database into RDS, or your heterogeneous migration from, a licensed edition of databases like SQL Server or Oracle to an open source MySQL or Postgres database. If you're doing a homogeneous migration, you could very well use native tools as well. For example, in SQL Server, it's pretty much easy to script out the entire schema without the data and apply that onto a target and go about with your database migration. Once you've prepared the target and your target has the empty schema ready, you could very well start moving your data using the DMS service. Or if you are migrating a data warehouse like Netezza or Greenplum or any of our other supported data warehouse sources, you could also use a feature called data extractors, which is available as part of SCT, to be able to move that data warehouse data into Amazon Redshift. Moving on, let's see how this service works. So let's say you have a group of application users connecting to your source database, which is in your on-premises data center. The first thing you would do is to start a replication instance. Then you would create a couple of entities called source and target endpoints. This is the way in which DMS is going to be able to connect to your source and your target databases. And then you create another entity called replication tasks, which are in turn going to run on the replication instance that you created in the first step. And it's going to utilize the source and target databases in order to migrate data from the source to that target database. And you either let DMS create the tables, or you could specify settings within the task to be able to migrate the data only. And once your target is in complete sync with the source, you should be able to switch your application users to that database that is newly created within AWS. And that's exactly how it's going to help you with near zero downtime migration, because the only downtime that you're going to face here is when the target is in complete sync with the source. You are going to have to shift your application users, stop the base home application, the source application, and shift your application users into the database running on AWS. So with that in mind, let's go into looking at what the migration playbook is all about. So like we talked about, each database engine has its own advantages, apart from the cost advantages that the open source flavors of these database engines offer. So the way in which your current applications might be working on a licensed database engine like Oracle might need some re-architecture when you go into an open source engine like Aurora Postgres. So when it comes to re-architecture, there are certain best practices that you would need to follow in order to understand how exactly the database engine in Postgres behaves, and how you could achieve your mission and vision of that application by changing them according to the industry-wide best practices. So we got this request at AWS. We base our entire roadmap off of customer requests. So when customers asked us ways and best practices to migrate their Oracle database into Aurora Postgres, we decided to publish a book. And the fruit of that book is the playbook that you're looking at. It's free of cost. You could go into aws.amazon.com/DMS, and you will find a PDF copy of this book there, where it's going to compare each and every feature available in Oracle and talk about the corresponding feature in Postgres, so that you can you know what exactly to do with a specific feature. And as we move on with this presentation, I'm going to talk about some of the top features that most customers normally use, and how those features are going to be implemented in a Postgres database engine, so that we're all on the same page with respect to what the best practices look like when you're trying to do a heterogeneous migration from an engine like Oracle to an open source engine like Postgres. So this book not only helps you with the feature by feature comparison, but it's also going to give you more details on how you could utilize plethora of other opportunities in the form of services at AWS with respect to other really cool services like Lambda, Kinesis, and everything else. So not only does it help you save on capital costs by trying to move into an open source engine, but it's also going to open up other opportunities within AWS for you so that you can remain ahead of your competition as well. So with that, let's move into the feature comparison like I promised and we talked about initially. So the first feature that I kind of wanted to touch upon today is materialized views. We all know how useful materialized views are because they are going to give you, more control over your data. You're going to be able to have a persistent copy of a certain query at any point in time in the form of a view, which is innately like any other table that you would like to have on the source. And you would like to run reports, or you would like to run other sorts of functionality achieved in Oracle by using materialized views. What we are going to do here is we are going to compare how materialized views look in Oracle and how they look in Postgres. So if you look at the syntax there, it's pretty much similar. So you clearly go ahead and create a materialized view called MV1 here, and you're selecting all the data from the employees table. Now, the actual difference between Oracle and Postgres comes when it comes to refreshing these views. So if you look at the second statement there, the CF parameter is configuring the refresh method where C is complete and F is fast refresh. So basically, when it says when you say it's a complete refresh, it's going to have to rebuild the entire view from scratch, and it's going to take in all the additions, like all the DML activities that happened on that particular table before it's going to be available to be accessed as a view. While fast refresh is like a dynamic refresh, where it's only going to take in the delta of changes that happened after you created the view initially. This is something that is available in Oracle. Unfortunately, this is something that is not available in Postgres yet right now. And if you have an application which is completely dependent on fast refresh views, you would have to re-architect your application so that you're independent of the fast refresh capability in Oracle when you try and move into PostgreSQL. So let's take a quick look at the comparison on how you would achieve the end-to-end flow of using a materialized view in Oracle versus Postgres. In Oracle, because of the way the views are designed, you would have to kind of execute that single statement that you see on the top left there, where you create a materialized view with fast refresh and fast refresh on commit, then the view is already present in Oracle and it's going to do a fast refresh when attempted. Now, the way in which you achieve the same functionality in Postgres is through a different manner. First, you'll have to create the view, and there are a couple of additional steps in order to achieve the same functionality. Once you create the view, you would create a trigger and a function in order to emulate refresh mechanisms. So basically, in order to emulate fast refresh, what you would have to do is create a function which is going to refresh that materialized view, and you have to create a trigger that is going to invoke this function to refresh the materialized view on any sort of DML activity. So basically, what you could also do is you could also have a cron job, which is going to control how many times or the number of times this trigger is fired on a particular database engine. And once it's fired, it's going to mimic the entire fast refresh capability that Oracle has currently. Now, some of the other advantages that Oracle has that are not available in Postgres yet is something called automatic incremental refresh. So in order to support automatic incremental refresh in Postgres, like I said, we'll have to create that cron job, which is kind of going to invoke that particular refresh trigger in order to make sure the views are refreshed in an automatic fashion. The other feature that I wanted to touch upon was the support for DML activity on a materialized view in Oracle. That is something that is not available in Postgres yet. So if you have an application which is dependent on that, you'll have to look at emulating it as a temporary table or other things like that in order to be able to perform DML activity so that your application runs fine as before. Now, moving on, let's quickly talk about partitioning. Partitioning, the very purpose of database partitioning is to provide support for very large table and indexes by splitting them into small pieces known as partitions. Each partition has its own name and definitions and can be managed separately from other partitions or collectively as one object. From an application perspective, partitions are transparent. Partition tables act the same as non-partition tables, allowing your applications to access a partition table using unmodified SQL statements. Table partitioning, it provides several benefits. First of all, it's a huge improvement in performance. It's going to help you improve query performance by accessing a subset of partitions instead of scanning a larger set of data, which is present in a single partition. When it comes to DDL operations, table partitions facilitate easier data management operations such as migration, index management, and rebuilding indexes. So Postgres started supporting declarative partitioning from version 10. And prior to version 10, partitions could be used via something called inheritance that we are going to go into via an example in the upcoming slides. The other item that I would definitely recommend looking into is Oracle supports various kinds of partitions like hash, range, list, composite partitions, whereas Postgres currently supports only list and range partitioning, even in the declarative partitioning that is happening from version 10. So again, even from version 11, this partitioning has been much improved, and I would definitely recommend checking it out on the Postgres documentation as well. So let's look at an example here of a list partitioning. So if you look at the create table statement there, I'm trying to create a table called system_logs, and I'm partitioning it based on a particular list. So errors 1, 2, 3 are going into table space 1 in its own partition called warning, and errors 4, 5, and 6 are going into table space 2 into its own partition called critical. Now, let's compare this partitioning example to how it is going to look like in a Postgres instance. So in Postgres, when it comes to list partitioning prior to Postgres 10, it is basically a 5-step process. When I say inheritance, the way partitioning is done is through a parent-child relationship. So firstly, you create a parent table, which is going to contain all of the data. And each of these partitions that you're trying to enable, be it list or range partitioning, is going to be created as child tables with check constraints. The check constraints are in there just to make sure wrong data from another partition does not come into some other partition. And then you create some indexes on the child table so that the query optimizer chooses to do an index seek when you're querying the child tables, because like we talked about, one of the biggest advantages of partitioning is to be able to query larger data sets in a fast manner. So those indexes are going to be very important on the child tables. And then you create a couple of things. You create a function to redirect data inserted into the parent table into the appropriate partition. And you create a trigger to execute that function once a DML event occurs on that parent table. So let's see these steps in action. So let's take the same system logs example that we were talking about initially for the Oracle use case there. I'm just going to create a base table, a parent table with called system logs with the required columns in there. And then when I create the child tables, I'm going to make sure my check constraints match the partition information that I gave in the parent table. I'm sorry, in the Oracle table initially. Like we talked about, we had errors 1, 2, and 3 in one partition, while errors 4, 5, and 6 were in a different partition. So we are just going to create two partitions called two child tables called warning and critical, and put those error codes in there with the check constraints to make sure those are the only values that can make it into that table. And now in the third step, I am going to create an index on that error code, because a partition is looked up based on the column you're partitioning on. So I'm adding an index on the error code column, which is the identity of this particular partition. And what we are doing next is to create that function that is going to handle inserting values into these partitions when we actually make DML events on the main table. For example, let's say I had a new insert with error 1. This function, when executed, it's going to make sure the entry with error 1 goes into the appropriate partition, or the child table, which is system underscore logs underscore warning in our case, and make sure it's logged both. It's there both in the parent table and the child table in general. And it's also going to raise an exception in case we are out of range in any of the partitions when we try to insert it in a certain child table there. But in Postgres, once you create a function, you would always try to follow it up with a trigger so that the function is actually executed upon certain events. That's the basis of a trigger. We're going to talk a bit more about triggers as we move on. But as a last step, what you would do in here is you create a trigger which makes sure that procedure in the previous slide is executed once there is a DML activity on the main table. So basically, once this entire setup is taken care of, it's going to make sure that when you insert it into the parent table, the data appropriately goes into its assigned partition, and you would be able to query the partition tables individually in order to achieve the performance benefits of partition in general. So let's move on and let's talk about triggers. So triggers are kind of similar in Oracle and Postgres. It's just that the implementation is a bit different. So you have different kinds of triggers in Oracle, like DDL, DML, and trigger on certain database operations. In Postgres, it's just two, but the second one is called event, which is collectively used for the triggers based on database operations and DDL in itself. And when it comes to different types, the advantage that Postgres kind of gives you is you'd be able to create a trigger for before or after events. So in case you want the engine to do something before an insert happens or after an insert happens, you'd be able to have that granularity of control in the Postgres instance. And at the same time, you also have the granularity of controlling these triggers at the row level or at each statement level. And here's how the comparison looks like. So when it comes to before triggers, basic DML activities, row level triggers can be used for tables and foreign tables, like tables which are involved in a referential integrity relationship there. And the statement level trigger can also be additionally used for views there. When it comes to the instead of triggers, like we said, Postgres, unless you do a refresh yourself or you utilize that trigger function methodology to provide that refresh capability, you would not be able to kind of manage it automatically like how Oracle does. So in order to maintain triggers on a view, you would have to use something called an instead of trigger. I would recommend looking at some of the examples online in order to understand a bit more about this instead of trigger. So this table kind of gives you more insight into the compatibility of triggers based on different database objects within the Postgres engine. So let's look at an example like we did for the previous features as well. So let's look at an example in Oracle. This trigger, what it's doing is it's called project set null. It's just the definition of the trigger. But what I want to make sure is project number is the primary key in the table called projects. And if there is a delete or an update for the primary key, I want to make sure it is updated to null instead of just removing the row or just updating the row in the first place. So basically, it's going to set, once there is a delete or an update, and once that is done, it is going to make sure it puts in a null number in another table and make sure the database administrator knows that there was an attempt to update or delete that particular row in the actual table. Now, let's look at a corresponding example of how we could achieve this in Postgres itself. Like we said, again, a function trigger methodology. You would have to create a function, which when it comes to Postgres, when you try to create a DML trigger, you'll have to create a function which returns a trigger, and you'll have to call that function via another trigger in order to mimic the actual functionality of a trigger. So in this example, we are trying to do the same thing, where once there is an update or a delete that is coming onto the primary key of that particular table, I want to make sure it is noted down, and I create an after update or delete trigger in order to execute this particular procedure, which sets that project number to null in another table, so that the database administrator is notified that there was some change going on for that primary key, for the entire row containing that primary key. So that was a quick overview of triggers. And now let's quickly look at how the sequences look like. I have an interesting example to share in the next slide. But in this particular slide, we are looking at the differences between Postgres and, not really differences, but we are just kind of trying to compare what is there in Oracle and what is there in Postgres. So if you see, most of the features that are available in Oracle are also available in Postgres with minor differences. And this table is also part of the playbook right there. So please feel free to read through the playbook. And if your application is heavily dependent on sequences, this is a reference table that you can look up in order to understand what kind of sequences Postgres actually supports at a particular point in time. Now, let's look at an interesting example that I learned from one of my colleagues who was trying to work on a Postgres migration from Oracle. So if you look on the left, this is a couple of sessions in Oracle, and on the right is a couple of sessions in Postgres. If you see the way the sequences are being created, it is starting with 100, incrementing by 1, and a set cache size in both Oracle and Postgres. Now, let's say we are using two different sessions, mimicking two different users connecting to the database. On the left, in Oracle, when you select the first sequence, because it starts with 100, it's going to give you 100. And if you are going to another session and you are doing a next value for that sequence, you're going to get a 101, irrespective of the fact that this is another session altogether, and irrespective of the fact that the cache size is set to 20 at a particular given point in time. And now when I come back to the original session, the first session, and I try to do a next value, it is not going to have any clashes, which is the way sequences are supposed to be designed. And it's going to give me the absolute next available value again, even across sessions. But it works a bit differently in Postgres. So in this case, what I'm trying to do is, with the same definition of the sequence, if I am going to create a value, the first value is 100, obviously, but if I am going to create the next value from another session, it's going to consider that cache size into account. It's not going to give me a 101 because it assumes that the first 20 numbers from 100 to 120 are reserved for session A. And 100 to 119 are reserved for session A, and it's going to give me the next value called, like you see on the screen there, 120 from another session. So what I guess I'm trying to say here is, based on the cache size, the kind of sequences that you will generate in Postgres are completely independent between sessions. And if this is something your application is going to depend on, you should be very mindful of this and work around this situation, because this is something by design in Postgres itself. So moving on to the next one, virtual columns. So basically, you would want to calculate certain column values based on other columns in Oracle, rather than storing them separately in a database table for space purposes, or just to make sure you get better performance out of querying that particular table. So Oracle innately lets you do that by design. So you cannot what you could do is you could base a virtual column and define it in a table and calculate it using aggregate functions or normal functions based off other columns. The other rule is you cannot create a virtual column based on another column, and you can explicitly specify a data type or let the database choose the data type. Now, how do we mimic this particular feature in Postgres? So Postgres does not have native virtual column support, but you can achieve virtual column support through views or something called function as a column. And if the only rule there is when you use a function as a column, it can be present as part of a select statement, like how we are going to look into an example right now. But it cannot, if you need the column to be part of an object, you must create a view, and that's how it works in Postgres. So let's look at an example to understand this better. In this particular case, this is an Oracle table. It's easy to create it. So basically, let's say in this particular company, the email is based off username, and it's just going to be at aws.com. So rather than having a separate email column, Oracle lets you create that with a lower of username and and append a concatenate operator that can be used as part of that virtual column there. And there is also another example in red right down there where I'm computing salary dynamically in the table and storing it. Now, how do we achieve something similar in Postgres? And this is how we do it. It's going to be a multi-step process again, but you would create the table without the virtual columns, because Postgres doesn't support virtual columns. And in order to mimic the virtual columns, you would create a function which is going to return whatever you need it to return. For example, in this case, it's going to take an argument within the function definition. It's going to get the username field from the table name that is part of that argument, and it's going to append at aws.com into it. Now, let's see how this works. So I'm in the step 3 there, I'm going to just insert some values into that particular employees table. And this is function as a column. So because I already created the function, it's going to recognize it as part of a column when I do a select statement, and it's going to invoke that function in order to give me the user email as in accordance to the function that we created. Now, if you already want it as part of the table, you unfortunately cannot do it quite as Oracle does it. So you would have to create a view in order to mimic the same functionality, and it's going to embed that particular results from that particular function into that view so that you can kind of query it as a table in itself. So a couple more features that I quickly wanted to touch on. Apologies for the text on the slide, but it's very important for us to know about this. So basically, the implementation of the number data type, synonymically it's called numeric in Postgres, is completely different. In Postgres, it can hold up to 131,000 digits before the decimal and more than 16,000 digits after the decimal point, which is much higher than Oracle. So the appropriate data type might seem like, for number in Oracle, might seem like it's a numeric, but the numeric field in Postgres is less efficient than the native integer or big-int fields in Postgres. So our recommendation is, if you're using the number data type in Oracle as a primary key or a foreign key, it is going to be better suited as a big int or an integer on the target Postgres instance as opposed to a numeric. And we've worked with multiple customers where we reduce the amount of CPU being used in Aurora Postgres from 100% to 20% because we made that change. So it's very important to understand that, the numeric is completely different from the way number actually works in Oracle. So one last part before we touch up quickly on SET is the differences in character sets. The biggest takeaway from this particular slide is Postgres unfortunately does not support UTF-16 at this point. So the n-varchar2 data type that Oracle supports, which specifically holds UTF-16, is something that is not supported in Postgres right now. So in case you do have some UTF-16 characters, you'll have to plan around that when you're trying to migrate into a Postgres instance. And when it comes to base character sets in itself, Postgres supports a variety of different character sets. It's really called database encoding in Postgres, and it's got support for both single byte and multi-byte languages. In Oracle, the way it works is you define the character set at the instance level or at the pluggable database level, while in Postgres, you can choose the encoding at database level, but you can also dynamically control the encoding. It's called the locale at the table or column level in itself. And similarly to Oracle, in case you wanted to change the in case you want to change the character set of a particular database, you'll have to do an import-export of the database or use the database migration assistant for Unicode in Oracle, which is something not available in Postgres. So it's going to have to be the base export and import to a new database. With that, let's quickly look at the schema conversion tool. A lot of the features I just talked about are something which were driven from application-specific testing decisions. So SET is a tool which can automatically help you take care of all these conversions itself. So basically what SET does is it's going to help you modernize your database tier when it comes to database objects in general, secondary objects in particular, from Oracle or SQL Server to Amazon Aurora, Postgres, MySQL, or other engines there. The biggest advantage, again, of SET is in case you're migrating your data warehouse schema, it's got something called data extractors, which can help you not only move those objects, but also help you migrate your data from the source schema like Netezza, Greenplum, or Vertica into Amazon Redshift. But the biggest advantage of SET is even before you go ahead with the conversion, like we talked about, heterogeneous migrations are hard. You would need to understand what exactly is going on, get to the root of the problem, and understand how the target engine is going to handle some of your workload there. So SET creates something called an assessment report, and it's an assessment of the migration compatibility of your source databases. So it recommends the best target engine, and it also provides the details of the level of efforts that you might need to take in order to convert some of those source commercial databases into open source database. Like we talked about, some of those features are not yet there in Postgres, but SET is going to recommend different ways of tackling those challenges and put you on the right path when it comes to migrating to an open source database there. So I would definitely recommend to check this tool out. It's a pretty updated tool, so we keep updating it every month with feedback we get from customers, and we try to push in a lot of improvements with every release. So definitely, once you start checking it out and once you start working on it, we definitely recommend updating it as soon as updates are available as well. So this is how the SET report looks like, and in this particular screen, you could see how we recognize issues and how SET kind of recommends changes along with links to the appropriate documentation. You would have complete control over your schema, and you will also have an editor built into the tool in order to edit in case you needed to edit any of these database objects. With that, thanks for all the attention during this webinar. I hope I was able to give you some details from my experiences on migrating from Oracle to Postgres. Please feel free to drop in comments, and we'd be happy to take any questions at this time. Thank you.